This video, we're going to look at predator-prey problems, and this could include many different types of predators and preys. We'll pick one example. We'll pick lions and gazelles to be our predators and our preys. So for our predator-prey problem, let's use gazelles and lions, and let's call X gazelles. And they're going to be our prey. And we'll call Y lions. They're our predator. And then, of course, the change in gazelles will be dx dt. And the change in lions will be dy dt. And like before, remember, we'll have like some rate of change, some R, which will be the net rate of change between the birth rate and the death rate. So we'll have like an R times X. The only thing we want to include, though, is we want to include the carrying capacity. Remember, if you have, like, say, a bunch of animals in a small area or in a forest or something, there's only so many of those animals that can survive there because there's limits in food and space and so forth. So we're going to have a logistics term here. And so times our rate of change, we'll have a logistic term, which is going to be 1 minus X divided by K. Let me call it K1, which is our carrying capacity. And then times X. Remember, for example, if you maybe have an area, a limited area, limited food, limited resources, you can maybe only maintain 1,000 gazelles in that area. So K1 would be maybe 1,000. And then notice what happens here is you get closer and closer to 1,000. In other words, if your number of gazelles X gets closer and closer to 1,000, this number is going to get closer and closer to 1. And then 1 minus that number is close to 1 is going to get close to 0. So our rate of increase is going to be very low. So as you get closer to the maximum capacity, this logistics term that they call, as they call it, will end up getting closer to 0. Then your rate of increase will be very low, or maybe even 0. And so that's what we have for the gazelles, and also for the lions. Well, it's kind of the same idea. Let me just call their rate of change R2, and it'd be 1 minus K2 times Y. Same idea. There's only so many lions that can survive in a certain area. And that's going to be its carrying capacity. Now, sometimes the carrying capacity could be very, very high, and as such that this term is going to be very small. And therefore, you can, in some cases, ignore it. If you have a really huge area that can maintain a lot of animals, it can maintain so many that you're never going to get to the maximum capacity. You could even make this term 0. Nothing we want to take into account is, again, the lions are the predators, the gazelles are the preys. So how do we model that? How do we deal with that? What kind of terms do we add to take care of that issue? So let's look at these different scenarios. Suppose you have many lions and only a few gazelles. Then there's not going to be too many interactions between the lions and the gazelles, and therefore not too many gazelles are going to be eaten. So So it depends upon how many gazelles and lines there are. Again, few gazelles, not many interactions. Same thing if you have a few lines and many gazelles. Once again, there's not going to be too many interactions. On the other hand, if you have many lines and many gazelles, then they're going to be coming across each other a lot. There's going to be many interactions, etc. So therefore, and let's just leave a space here for the moment. Therefore, the number of gazelles that are going to be consumed by the lions depends upon the number of lions and the number of gazelles. So we can represent that as x times y, like this. But that's going to have to be times some constant. And for the moment, let me just call that C1. And we'll put a negative here. So what this is saying, the more lines and gazelles there are, it's going to be x times y, gazelles times lines. The more interactions and the more gazelles are going to be eaten. Therefore, that's going to be negative. In other words, it's going to be a negative effect on the rate of change of the gazelles, because remember, dx dt is the rate of change of gazelles. So there's going to be less of them the more interactions they are, but it's going to be proportional to some constant. Now we really don't know what that constant is, and sometimes we'll figure that out later. Now another thing that will happen, again, the more interactions there are, the lions have more to eat, and their rate of change is going to increase. They're going to have an increased number of lions based on the interaction of the gazelles and the lions. Now, notice that we have two different constants here, because just because, you know, a lion eats a gazelle, it doesn't mean it's going to, the number of lions is going to have an increase of 1 or anything like that. So the rate of decrease of the gazelles due to the interactions is not going to be exactly the same as the rate of increase of the lions due to the interactions. So they're going to have to be a different number. So we get something like this. And let me just rewrite our system. And let's multiply things out here a little bit. And dx dt is going to be R1 minus, and let me actually put the x in here, R1 minus R1 over K1 x squared minus C1 x y, like this. Dy dt is going to be R2 y minus R2 K2 y squared plus C2 xy, like this. Now we can maybe simplify our constants just a bit. We can make these dx dt, and let's maybe call this R1. We're going to call that A1x, and we'll call this one over here B1 x squared, and we've already named that C1 xy, and then dy dt. We'll call this a 2 times y. Does that look like a y? Let me fix that. Minus b2 y squared plus c2 xy, like that. And so we're here. Where a1 is equal to r1. Now, again, you don't have to do this. I'm just maybe kind of simplifying these constants. And then b1 is equal to r1 over the carrying capacity. Remember, this is the maximum amount of animals. And then c1 is just c1. That's going to be the rate of decrease of the gazelles due to interactions. Then over here, a2 is r2, and b2 is r2 over k2, like that. And so there's our system. So let's take a look at this example. We want to make a system of ordinary differential equations. That is a predator-prey system of differential equations that represent gazelles as the preys and lions as the predators. And we're given this birth rate. The gazelles have a birth rate of 1.3 per year. Gazelles have a death rate of 0.35 per year. I'm not sure how close these are. If you wanted to actually do a problem like this, you could probably look up maybe more exact numbers. And the lion birth rate I have put down as 1 per year, and the death rate as 0.8 per year. Once again, these are really just estimates. And suppose they're in a area that can accommodate 10,000 gazelles and 8,000 lions. So that's going to be like the carrying capacity. And finally, the C1 term. This is the C1, C2 term. These are really the most difficult terms to estimate. So I just picked these numbers. Again, they're just rough estimates. And again, remember what they mean. If we look at our differential equations, C1 indicates really the number of gazelles that are eaten by the lions, or I should say the proportion of gazelles that are eaten compared to the number of interactions. And again, say if the gazelles are very fast, then this number is going to be small. Even though there's a lot of gazelles and lions interacting, if the gazelles are able to get away, this number will be very small. On the other hand, if the lions are able to catch them a lot, then this number is going to be bigger. So I put this number down as 0.0005. Again, that's just just pulled out of the air, just an estimate, just to kind of show how to set up the model. And the same with the C2 is an estimate. This is the increase of the number of lions based on the interaction of the lions and the gazelles. We have is that. And then finally, the initial condition, we'll estimate, let's say we have an area where we know the initial number of gazelles is 1,000 gazelles at our starting time, and let's say 200 lions. Like this. So again, if you want to stop the video to write all that down, you can. If not, we'll go ahead and take a look at this. So again, we're using this system of differential equations here. So now we're going to need our rate, our net birth rate. So in our case, that's going to be this 1.3 minus a 0.5 for the gazelles. So remember, that's a net birth rate. So it's going to be R1 is 1.3 minus 0.35. It looks like that's 0.95. Or you could just put it like that into the equation. Wouldn't really matter. And then the line birth rate is R2, which is 1.0 minus 0.8, 0.2. And the carrying capacity for the gazelles, remember that's our K1, and that's 10,000. And our carrying capacity for the lions is K2. 800. And finally, the C1 and C2. Let me just write them down again over here. C1 is 0005. C2 was 00003, like this. And looks like we have everything we need here. So let's just go ahead and put everything into our equation. Again, we said this is the same as R1 and R2 is the same as A1 and A2. Let me start by putting those into our differential equation. That. And our B1 and B2, the B1 is R1 over K1. I'm just going to actually keep it in the equation like that. Like it's, so that's that term here for B1, or if you could divide it out and put it, it's up to you. And that's going to be times X squared. And then we have the C1 term, which we have up here. That should be a minus. Then B2 was R2 over K2. And then finally our C2 term. Oh, by the way, up here, I forgot something up here. Please fix this. This should be X times Y, X times Y, like this. And finally, the initial conditions, 1,000 gazelles and 200 lions. So remember the gazelles are the X, and that's going to be 1,000, and the initial condition for the lions is 200. So there's our system of differential equations right there. And this is our initial condition, so it's really going to be all this. And that's it. That's our system of differential equations for this example. And that's if you want to do analysis on this, like for null clines and things like that, you can watch the video link below. And also to put systems in the MATLAB and solve them with a MATLAB solver, that video is also linked below. But in this video, we're mainly focusing on just setting up the predator-prey problems and understanding what they mean. So the question is, how would the model change? How would our predator-prey model change if the predators were egg-eating predators? And this is the case, for example, with certain snakes. Certain snakes will eat the eggs of the prey. So let's take a look at that. And so actually the final result is going to look the same. It's just going to be interpreted a little bit differently. So let's take a look at this here. So now, just like we did before, we'll have our rate, our birth rate of each species. Again, remember this rate here is going to be the net difference between the birth and death rate. And just like before, we're going to have a carrying capacity. And now we could think of the fact that the predators eat the eggs of the prey. That would decrease the rate of increase of the prey. For example, remember this represents the birth rate minus the death rate. So this is the net birth rate. And if the predators are eating the eggs of the prey, that's going to reduce this rate of increase. And so it could be like a minus. So now, again, suppose the predators are eating the eggs of the prey. Now that will reduce the birth rate. In effect, it would reduce the birth rate of the prey. So we can have a term here that's going to reduce the rate of birth of the prey. So we could maybe call this, let me just give it another letter. Let me call it W1. You can really pick whatever you want here, times Y, which is the number of predators, times X. So again, let's review what we have here. Remember, normally this term is going to be the birth rate times the number of prey there are around. And then we reduce this based on the carrying capacity. But now we're also going to reduce this based on the fact that the predators are going to eat the eggs of prey. So that's going to also reduce the birth rate. And now for the predators, you could write it pretty much the way we had it before. Or if you wanted to, you could kind of also reinterpret that in terms of the rate of change. Now, for the predator, you don't have to, but you could maybe interpret that as, say, you would be increasing the birth rate of the predators as they eat the eggs of the prey. Now, again, this time, this would not be really different at all from what we did before, because whether the predators are eating the prey or the eggs of the prey, it's really all going to be the same. But you'll notice, though, even though we're interpreting these different, let's multiply things out, and we'll find that we're going to get the same thing we had before. So let's say if you did dx dt. Now, when we multiply everything out, we get these two differential equations. And we can now finally assign these other letters. And so we could, similar to what we did before, we can make this, what did we call this before? We called this A1x minus B1 x squared. And now let's call R1 times W1, let's call that C1 xy. And then dy dt is going to be A2y minus B2 y squared plus C2 xy, like this. And now, so it's similar to what we had before, except we're just defining some of these a little bit differently. B1, A1 and B1 are the same as before. The one thing that's slightly different is this C1 is R1 W1. B2 is R2 over K2, and C2 is R2 W2, like this. So you can see we actually ended up with the same form of equation that we had before, except just now that especially really only this one term here is interpreted just slightly differently. Before, this quanta was based on the interaction of the predator and prey, and now it's based on the rate of change, birth rate of the prey, and the interaction the predator has with the eggs, but the form of the equation is exactly the same. Now, of course, with these equations, now notice in this one here, you can factor out the x. In this one, you can factor out the y. Or, again, you could have just started with the way it was here. And you could do lots of analysis on this system, find critical points, equilibrium points, that is, and the nullines. And so you can do lots of analysis from this point on. Now, in another video, which is linked below, it'll show you how to do the nullines on a system like this. So if you want to find the nullines, equilibrium points, and so forth, I go to that video.